Hello everyone, today let's solve the problem number 230. Kth smallest element in a binary search tree. So what the question states here, given a binary search tree BST and an integer k, right? So we have been given a binary search tree here BST. So this one root we can clearly see here, right? This is BST, right? So to be the valid BST, we know that. So the left subtree's value has to be lesser than the root and the right subtree value has to be greater than the root, right? So given, they have not mentioned balanced BST, they have just mentioned given a binary search tree and an integer k. We have been given integer k here, so we have to return the kth smallest value in the binary search tree, right? So they have given, we have to return the kth smallest value in the BST and it has one index, they have said, right? So here let's come to the first example. So just give me a second here. We have 3, 1, 4 and 2. So k they have given 1, means one index they have already mentioned, means first smallest element we have to return. In this case we have 1, 2, 3, 4 when we sort, right? So we have to get the we have to return the value 1 as it is first smallest element here. See here, right? So we have got 1 here. This is fine. Let's move on with the second example here. Just give me a second here. Yeah, we have this one 5, 3, 6, 2, 4, 1 null. Yeah, this one null we have. This is fine. So we have been given 5, 3, 6, 2, 4 null 1. This is fine. So output, so k equals 3 they have given, means third smallest element. So we have 1, 2, 3, 4, 5, 6, right? So the third smallest element is 3 here. In this case we have to return 3. That's what they have given as output. This is fine. So this is the output that we have to return. I hope the question is completely clear. What we need to do is completely clear as well. Easy to understand, right? So let me clean up this one. Just give me a second. What did I do? So yeah. So let me clean up this one. So yeah, this is fine. Initially, let's discuss the approach and then followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. So the first thing that we need to keep, note down here as iterative in order traversal. We are going with the iterative in order traversal. So we are going, we are dealing with the iterative in order traversal using stack. This is fine. So iterative in order traversal using stack. This is fine. So the first example, I have considered the same example, the first example that they have given in the question, right? 314, this one null 2. This is fine. Root 314 null 2 we have been given here. So out, this one k equals 1, output has to be 1 because 1 is the first smallest element here. So we need to return the same. We have already discussed this one. Don't get confused, right? So let's move on with the second, step by step execution, right? So first, what we will do, we will start. We are going with the iterative in order traversal using stack. Just keep this in mind, right? So in order, when I say in order traversal, first we are going with the left element order. I'm just saying. So left, root, and then right, right? Left, root, and right. This is the order we'll be performing in the in order. We should be knowing this. Whenever you are solving the problem in trace, have a thorough knowledge on recursion, BFS and DFS, and traversal. When I say traversal, 3 type of traversal I'm speaking of. Basically, this one, in order traversal, pre-order traversal, and post-order traversal, right? These 3 traversal, just keep this in mind, right? So I'm just speaking of this. So have a thorough knowledge on these things, right? First thing is recursion, BFS, DFS mainly, and traversal. This thing, in order, post order, and pre-order, and a different type of trees as well. BST, binary search tree. This one, heap, max heap, and min heap, as well as binary tree, all the trees. So just have thorough knowledge on that one. Just go through the examples and just see how it works, right? So just have thorough knowledge on these things. So first thing here is we will start at root 3. First one, this one I'm speaking of. we will start at root 3. So we will move left to 1. We will move left to 1. This is fine. We are moving left to 1. Then which is equal to null means we will backtrack, right? We will backtrack. Then we will visit node 1 means first smallest. We will visit node 1. First 3 we will start from 3. Here this one. So we will move to node 1. We will visit node 1 first smallest, nothing but k equals 1 here. We have been given k equals 1, right? So therefore we will return 1 in this case. Therefore we will return 1 in this case, right? So this is it, right? So the value that we got here is 1. The output that we got here is 1, and the output that they have given for the example 1 in the question is also 1. So these two are 1 itself. In this case, these two are 1 itself. The approach, so the output that we got is equivalent to the output they have given for the question. I mean example 1 in the question, right? So the approach works absolutely correct in this case, right? So approach works absolutely correct in this case. So and now we are completely familiar with the approach. Let's discuss the edge cases one by one very quickly, right? So the first edge case here is for the single node tree, right? We are dealing with single node tree. Here we have only one node, 5. This one, this is fine. Just give me a second here. So here we have only one node, 5. You can clearly see here. K we have considered 1 here. K we have considered 1, and the output is 5 here in this case. The output is 5 because we have only one node, and k equals 1. The smallest, kth smallest element here is only 5 itself. The first smallest element here is 5 itself, right? That is the reason we are returning 5 as output. So the next one is right skewed tree. Right skewed tree, you have to know, by this time you have to know left and right skewed tree, right? We have been given root here, in this case 1, null 2, null 3, null 5 means 1 right skewed tree, right? 2, 3 and 4 here. In this case we have the value 1, 2, 3, 4, right? So we have been asked to find the third smallest element here. Among the 1, 2, 3, 4, 3 is the third smallest element. We have to write on the same. Let's move on with the third edge case here, left skewed tree. So we have been given here 4, 3, 2 and 1, right? So same, we have the values here 1, 2, 3, 4. We have been asked to find the second smallest element. In this case 2 is the second smallest element. We have to return 2 itself in this case. Let's move on with the fourth edge case here. Complete balanced binary search tree. Complete balanced binary search tree here in this case, right? We have 1, 2, 3, 4, and we have been asked to find the second smallest element. Second smallest element here is 2 because we have the values 1, 2, 3, 4. We have the complete BST. This is similar to the first example that they have given in the question, right? So, but we have been asked to find the second smallest element here. In this case, 2 is the second smallest element, right? So, these are the 4 edge cases that we need to keep in mind. First edge case is for single node tree. The second edge case that we discussed for is for this one, right skewed tree. The third edge case that we discussed is for left skewed tree, and the final edge case or the 4 edge case that we discussed is for the complete balanced binary search tree. This is fine. These are the 4 edge cases that we need to keep in mind, right? So this is fine. Now we are completely familiar with the approach as well as the edge cases, right? Now we are completely familiar with approach as well as edge cases. So as we are completely familiar with the approach and edge cases, now we are good to write the code. Let's start writing the code. The first thing here is we have already discussed this one. I said we'll be making use of the stack for in order traversal, right? So let's make use of the stack here. So I'll just give here type integer. Sorry, we are making use of the tree, right? This has to be tree node. So I got confused here. Just give me a second here. Going with the tree. So this is fine. Tree node. So I'll just give here stack equals new stack. This is fine. New stack. So we are just making use of the stack for the in order traversal. So we need a pointer to traverse the tree. Also, we need to count the nodes that is being visited, right? So let's initialize here current. So let's assign the current to root. or let's initialize current to root here in this case, and also let's initialize count to 0, count variable to initially 0, right? This is fine. So next step here is we have to iterate. So we have to iterate while the nodes exist. Only when the nodes exist, we have to iterate till the nodes exist, right? So that is the reason I'll be making use of while loop here. While current not equal to null in this case. So what we need to do here in this case? So sorry, we have to write one more this thing. I think more condition. I think just give me a second here in this case. When current not equal to null and out of stack dot is empty, so stack shouldn't be empty, right? In that case, so then only we can iterate. So then only the elements will be found and we can iterate through each element, right? So that's what here we have to go to the leftmost node. So I'll be making use of while loop again, leftmost node, because we are making use of we are going with the in order traversal, right? While current not equal to null. This is fine. I'll just go with within this one stack dot push of. I'll just be making use of the push operation here. Push of current. Current equals current dot left in this case. This is fine. So the next step here, we have to visit the node first. So current equals this one stack dot top. Right. This is fine. We have to visit the node. So we'll just increment the count after visiting the node, right? Particular node. So after this step, if kth node is found, means if the kth smallest element, whatever they have mentioned, if kth node is found, then we have to return the value. We have to return that particular value, right? Right. So we can write in this way: if count, if it is equal to k, we'll compare with the k. If it is equal to k, then we will return the value of the current. I'll just give here current dot value. So we have to then after that one, now we have visited left root and we have to visit the right subtree as well of the root, right? So I'll just give here, we have to visit the right subtree. I can just give here current equals current dot right. So this is it for the code. So one more step. So if not found, it shouldn't happen in the constraint basically. If not found, then we have to return -1, right? So accordingly with the constraint, it shouldn't happen. But still, let's give here. If not found, this one, we will return -1, right? So this is fine. This is it for the code. Let me format the code once and let me hit the run button. So now you can clearly see the sample test cases are getting passed, right? Here the sample test cases are getting passed. Means the code works absolutely correct in this case. Let me hit the submit button. Let's see whether this works for all the test cases or not. So you can clearly see here all the test cases are getting passed. Means the code works absolutely correct in this case, right? So as the code works absolutely correct, now let's quickly discuss the complexities for the code that we have written. So first thing we have to know here is we already know this basically. So the approach that we went with here is iterative in order traversal, that is using stack. We know this one, right? Iterative in order traversal using stack. So what is the overall time complexity here? The overall time complexity here would be big O of n, right? Big O of n, or we can just give here big O of h plus k. So let me consider here big O of h plus k. I'll say why I have considered big O of h plus k. For the best case, or for the best this one balanced binary search tree, it is logarithmic n, big O of logarithmic n. We know this one. For the worst case, so left skewed or the right skewed tree. For the worst case, it is big O of n, right? So we can just consider the overall time complexity as big O of h plus k, where h is nothing but tree height, k is nothing but number of the elements that is being visited. So that is the reason I have given here big O of h plus k, right? So what would be the space complexity here? The space complexity would be big O of h in this case, right? So h is nothing but height of the tree. So again, we know that for the worst case, it is big O of n for the skewed binary search tree, and it is logarithmic n or big O of logarithmic n for the balanced by this one binary search tree. So let's consider height of the tree, nothing but h here as space complexity. complexity, right? So the overall time complexity is big of h plus k, and the space complexity is big of h for the code that we have written. I hope whatever the code that we have written is completely clear as well, right? For now, this is it. Thanks for watching, guys.